All right, let's take a look at a few more trig integrals here, and then we'll actually take a look at a few e to the x and natural log of x integrals as well. So first, let's just review all of our derivatives of trig functions. So here are our six basic trig derivatives. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared, derivative of secant is secant times tangent, derivative of cosecant is negative cosecant times cotangent, and derivative of cotangent is negative cosecant squared. So whenever we're looking at integrals, right, we want to look at going backwards. So whenever something like this shows up, we can go backwards, okay, and say that the antiderivative of sine is negative cosine. Okay, if the derivative of cosine is negative sine, we can say the antiderivative of sine is negative cosine plus c. Right? Similarly, we can say the antiderivative of cosine is sine, the antiderivative of secant squared is tangent, the antiderivative of cosecant squared is negative cotangent, the antiderivative of secant times tangent is secant, and the antiderivative of cosecant times cotangent would be negative cosecant. Okay, so we're just thinking about undoing all of these trig derivatives, okay, going backwards. And then don't forget your plus c's. All right, so real quick, let's just take a look at a couple of examples here. So, for example, if I give you something like, I don't know, the integral of 2 secant squared of x. Okay, well, we know that the antiderivative of secant squared is tangent. Okay, whenever we have a coefficient out front, remember, one of our properties is I can just pull that out in front of the entire integral and just tack that on to my answer. So here, we could say that the antiderivative of 2 secant squared is just 2 tangent of x dx. Oops, that's not right. 2 tangent of x plus c. There we go. Okay, remember, when we integrate, the dx goes away. All right, so another quick example about the antiderivative of 6. Let's do negative 6. Negative 6 cosecant of x cotangent of x dx. All right, well, if the antiderivative of cosecant cotangent is negative cosecant, I will end up with a double negative. Right? So the antiderivative would be positive 6 cosecant of x plus c. All right? Pretty straightforward, okay, but we do need to be able to recognize these, okay, which is why we need to have our trig derivatives memorized. Okay, we'll probably have another memorization quiz here soon. Okay, these are very important to have memorized. Okay, now something else that could show up would be something like this. If I ask you for the antiderivative of 1 over, let's say 1 over sine squared of x dx. So this looks like a pretty daunting problem right off the bat. However, we can rewrite this and make it a lot easier, just like what we did in the lesson yesterday, okay, when we were rewriting polynomials. I can rewrite trig functions as well. The most common identities that we'll use are the reciprocal identities. So 1 over sine squared is the same thing as cosecant squared. Right? So I could say this is the same as cosecant squared of x dx. Now, that's pretty easy to take the antiderivative of. Right? The antiderivative of cosecant squared is just negative cotangent of x plus c. All right. So always, always, always keep those reciprocal identities in the back of your mind. Okay? If you forget them, look them up. Okay? Sine and cosecant are reciprocals, cosine and secant are reciprocals, and then tangent and cotangent reciprocals of each other. Okay? So keep that in the back of your head. So you guys try this one then. About the antiderivative of 1 over secant of x dx. Well, 1 over secant is the same thing as cosine. Right? So this would become the antiderivative of cosine of x dx. And the antiderivative of cosine is just sine of x plus c. Okay, so make sure you understand this step, we didn't do any integration. Right? All I did was use my reciprocal identity to rewrite 1 over secant as cosine, and then I took its antiderivative. Okay? So we'll do a little bit more practice with this in class tomorrow. Just one other short idea then. We know the derivative of natural log of x. Okay? The derivative of any log is the derivative of the inside over the inside itself times the natural log of the base. So here, remember, the inside is x, so the derivative of x is 1 over the inside times the natural log of the base. The base here of a natural log is e, but the natural log of e is just 1. So I can say that the derivative of the natural log of x is just 1 over x. Right? Similarly, okay, if I have the antiderivative of 1 over x dx, I can say that the antiderivative of this is equal to the natural log. Now, I did actually forget to mention something in our lesson yesterday. Okay? Whenever we take the antiderivative and we get a natural log, we need to put absolute value bars, because in this function, I can plug in any value of x. Right? I could plug in -17. I could plug in 1,000. It'll work, except for 0. In this function, okay, I cannot plug in any value. Right? If I plug in -7, if I didn't have the absolute value bars, I can't take the natural log of a negative number. So whenever our antiderivative is a natural log, we need absolute value bars. Okay, there's a little bit more complicated mathematical explanation, but we're not going to get into that there. Okay, just remember that whenever a natural log or any log is your antiderivative, you need to put absolute value bars around whatever you're taking the log of. Now, we also have that the derivative of e to the x was, well, the derivative of any exponential function is the exponential function itself times the derivative of the exponent times the natural log of the base. So, in this case, the derivative of e to the x is just e to the x. Well, that makes finding its antiderivative pretty easy, right? That means the antiderivative of e to the x dx is just e to the x plus our arbitrary constant. Okay, so we can take antiderivatives, okay, whenever we see something like 1 over x or 7 over x, and e to the x pretty easily. So, for example, if I give you the antiderivative of 5 over x minus 6 e to the x dx. Okay, well, we can take this piece by piece, and we can say, well, 5 over x is the same as 5 times 1 over x, right? So, we know the antiderivative of 1 over x is natural log of x. So, actually, let me rewrite this here using our properties. So I can say this is the same as 5 times 1 over x dx, and then pull that -6 out. So minus 6 times e to the x dx. Okay. Sometimes students get confused and think this 5 should go on the inside of the natural log, but if we see how we use our properties here, if I pull that 5 out, we can clearly see that that 5 will go out in front of the natural log like this. Okay, well, 5 times the natural log of the absolute value of x minus 6, the antiderivative of e to the x is just e to the x, and then plus c. All right, so how about you guys try this one? About the antiderivative of 2x cubed minus 6 over x plus sine of x plus e to the x dx. Okay, that's quite a function. Take the antiderivative of that. All right, well, let's just go piece by piece. So the antiderivative of 2x cubed would be, well, add 1 to the exponent, so x to the 4th, and then take the old coefficient over the new exponent. So that would be 2 over 4, or that would reduce to 1 over 2. Then here, this would be minus 6 times the natural log of x. Then the antiderivative of sine is negative cosine, so minus cosine of x. And the antiderivative of e to the x is e to the x, so plus e to the x. And then don't ever forget your plus c. All right, so we will do a little bit more practice with these trig functions and basic logs and exponentials tomorrow in class.